Hello and welcome to Snippets for Statistics. Today's lesson is on the chi-square test of independence. The chi-square test of independence is a non-parametric test. It doesn't use parameters. It doesn't use numerical scores for each individual in the sample. It relies on the chi-square statistic. It uses sample data. It does not state the hypothesis in terms of a specific parameter. Hypotheses are about the entire population. It makes few, if any, assumptions about the population distribution. The data are frequencies. So the chi-square test for independence has two types of hypotheses, two types of null hypotheses. Version 1 looks at the data as a single sample. Each individual is measured on all variables. This is sort of like a correlational study, so you can compare the different variables for a single individual. Version 2 uses two or more samples from two or more populations and basically asks, are there differences between the two populations? And this is more like an independent groups t-test or single factor ANOVA. The chi-square test for independence is similar to the test of goodness of fit. We look at observed frequencies and compare them to expected frequencies for each category, and our calculation is very similar. We have our sample, a set of observed frequencies. We have our null hypothesis, which is used to generate a set of expected frequencies. And then we use the same formula that we used for goodness of fit. Chi-square equals the sum of the differences between our observed and our expected squared over the frequency of the expected values. The steps for computing a chi-square test for test of independence are similar but slightly different. As before, we state the hypothesis and select an alpha level. We find the critical region based on the degrees of freedom. For chi-square test of independence, the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. We calculate chi-square by selecting a sample and counting the observed individuals in each category. And we construct a hypothetical sample with each category. That gives us our expected values. Then we're going to compare the two. So we're going to compare and calculate chi-squared obtained. And of course compare chi-squared obtained with chi-square critical and make a decision based on the hypotheses. So this is an example from the textbook, an example that looked at the differences in type A versus type B people. Type A tend to be more competitive, driven, pressured, and impatient. Type B are less competitive, more relaxed, and less likely to have heart disease. So they were measuring whether they were type A or type B, the frequencies of whether they fell into that category, in a random sample of individuals. And they were examined and categorized as to whether they have a heart disorder. So what we're given here are the actual observed frequencies. So type A and type B are listed on the left side. No heart disease and heart disease are listed across the top. So each individual fell into one of those four categories. So we had a total of 200 individuals in this sample. 32 were type A, no heart disease. 18 were type A with heart disease. 128 were type B with no heart disease, and 22 were type B with heart disease. The values on the far right side and the bottom are actually the totals. If you add up 32 and 18, you get 50. 128 and 22, you get 150. And if you go down, 32 plus 128 equals 160, and 18 plus 22 is 40. We'll see how those values are used in just a bit. First, we state the hypothesis. There is no relationship between personality type and heart disease. So we're assuming that there is no effect, there's no difference. And essentially, remember, we're looking at this like a relationship. Each individual is measured in two ways. The alternative hypothesis, there is a relationship between personality type and heart disease. We're going to find the critical region based on degrees of freedom and based on the number of cells and alpha level. But we'll get the degrees of freedom based on the number of cells and alpha level. We have 2 rows and 2 columns, so our degrees of freedom are row minus 1 times column minus 1, which is 2 minus 1 times 2 minus 1, which is 1 times 1, and that's 1. Using our table in the text for alpha equals 0.05, we find that chi-square critical is 3.84. Now what we need to do is derive our expected frequencies from our observed frequencies. This is a little different than we did for the goodness of fit. We're going to actually figure out what our expected frequency should be based on the number of people who participated. So we're given the observed values, and we need to figure out the expected values. The text provides the row and column totals, but we're going to explain how they got derived. because they're not always given. So the table that we originally would get is like this. This shows us the data, the observed data. Well, we find the row and column totals by adding the values along each row and across the columns. So that gives our row totals. And then we compute the column totals by adding the values along each column across the rows. There are our column totals. Same values we had before. Now what we do, we get n from adding either the row or column totals. So we have a total of 200 people in this study. So now we can create our table of expected frequencies based on our computed row and column values. This is how we do it. We use the formula F sub e, which is expected value, equals the frequency of the columns times the frequency for the rows over n. So what we do here is we start with just the row and column totals. We leave the table empty. We're going to create a second table. We're going to keep the first table we had before, but now we're going to create a second table using just the row and column totals. If these values are consistent, we just go ahead and find the values of the cells for any population, assuming that the row for type A is 50, the row for type B is 150, the column for heart disease is 160, and the column for no heart disease is 40. So let's calculate. There we go. We get our heart disease for type A, that calculated from 160 times 50 over n, which is 200. We do that for the other columns as well, for the other categories as well, the other cells, as well. Get the values there: 40, 10, 120, and 30. These are the values we should get if the data comes out just using the row and column totals that were given. Now we go ahead and compare expected frequencies and observed values. So we use the two tables. First we have the observed frequencies. These are what we were given in the problem, and then the expected frequencies that were computed. So here are our observed frequencies, and here are expected frequencies. And we're going to compare the similar cells in the two tables. There are 4 cells. So basically we're going to compare the observed value for type A heart disease with the expected value for type A heart disease. Same thing for type A no heart disease in observed and expected, and the same as the other categories as well. So we use this formula, and what we get is this. This is again, we are comparing for each sum, for each thing we're looking at. It's the observed frequency from the observed table minus the expected frequency for that same cell squared over n. Over the expected frequency. Over the expected frequency. Remember, this is the same formula we used for goodness of fit. So observed frequency minus expected frequency, that value squared over the expected frequency. We add all of those up, and that gives us chi-square obtained. And in this case, chi-square obtained is 10.67. Now, we go ahead and compare it to the critical value and make a decision. As you recall, our critical value was 3.84. Our obtained value is 10.67. We need to know, is 10.67 greater than 3.84? Okay. Since obtained is greater than critical, we can reject the null hypothesis, that's the null hypothesis, and state that there is a relationship between personality type and heart disease. You can calculate effect size using something called Kramer's V. This formula is a little messed up on here, it's a little hard to read, but V equals the square root of chi-square over n times degrees of freedom, and there's an asterisk there. The degrees of freedom asterisk is the smaller of row minus 1 or column minus 1. In a 2 by 2 matrix, though, you can use the special version for the phi coefficient because degrees of freedom equals 1 and drops out of the calculation. This is just a side note, but it is a way to calculate effect size. From the example, we get, in this phi coefficient, you'll notice, because we did a 2 by 2 table, it's chi-squared over n, which is the square root of 10.67, which is our chi-square value obtained, over 200, which is our n, and that gives us a value of 0.23. And we can make a determination about the effect size using table 18.10 in Graviter and Wallnow 8th edition. There are other tables in later editions as well, too. But for degrees of freedom equal 1, for 2, and for 3. So we can determine 0.23 for degrees of freedom equals 1 that is somewhere between a small and medium effect size. Okay. And that concludes our lesson on chi-square test of independence.